So today we continue with Hilbert spaces. So we had seen we saw the definition last time of a scalar product. Then we were proving this theorem here, and we proved that there exists U star in K which satisfies this first equality here. And so now we are going to prove that, in fact, this is equivalent to this one here. So first we want to prove that if U star satisfies equality 1, then it satisfies the inequality 2. All right, so we have, what do we have? We have that U minus U star is less than U minus V for all V in, sorry. Yeah, it's for all V in K. Okay, so what I'm going to introduce here, I will use the fact that my K is convex. So I can always say that so let's assume that I pick up so U star belongs to K. So if I choose some combination, some convex combination between U star and the W for so let's say here I will put that. We will have that. So this belongs to K. Because what? Because why? Because K is convex. So I can say that U minus U star is less than U minus 1 minus T U star plus T W. So of course T belongs to the interval 0, 1. All right. And of course, here I need some parentheses. All right, so I obtain that u minus u star is less than u minus u star plus t, and here u star minus w. All right, I just distributed here the minus, and that's what I obtained. All right, so I can also take the square here. Okay, but by so what's the definition of that is exactly the product scalar, so the scalar product. So by definition, this is okay. So what do I obtain? I obtain that I will distribute. I will obtain u minus u star square. I chose things in purpose, so to obtain this one, so it will cancel with the left hand side of the inequation. Then I will get plus 2t u minus u star minus w, and finally plus t square u star minus w square. So let us rewrite this equation. So just notice that well, this cancels, right? Okay, so I obtain that two g u minus u star minus w plus t square u star minus w square is non-negative. So for t positive, I can divide by t, and this implies that 2 u minus u star minus w plus t u star minus w square is non-negative. So now, taking the limit as t goes to 0, we obtain that u minus u star minus w is non-negative. And that's what we want. So next, what do we want? We want to do the other way. So next, we assume that this one is true, and we want to prove the one. So let's have a look at u minus w square for w, which is in k. So since I have an information with U star, I'm going to introduce U star here. And so since this is defined thanks to a scalar product I obtain, so I obtain U minus U square plus 2U minus U square minus W plus U star minus W square. But here, sorry, this is non-negative. This is non-negative, so this is larger than U minus U star. And so that's it. All right, so next, we want to prove that if such a U star exists, it is unique. So as usual, let's pick up two such points in K. So assume that U1 star and U2 star both satisfy 2. All right, so we have that V minus, sorry, so it's U minus U star, V minus U star, or V, K, and U minus U2 star, star V minus U star, let's write it double, is less than 0 for all W in K. What I'm going to do here, I will replace here. I will choose here U2 star, and here I will choose U1 star. So in particular, we can write that U minus U1 star, U2 star minus U1 star is non-positive, and U minus U2 star, scalar U minus U star, is non-positive. And now I will sum up these two. So I will, so summing the two, so just multiply this by -1 and this one also by -1. So I will obtain U minus U1 star minus U plus U2 star. And here I obtain U2 star minus U1 star is non-positive. All right. And so this gives U1 minus U2 star square, U1 star minus U2 star square is non-positive, which implies U1 star equals U2. And we're done with the proof. So, so this U star from the theorem is called the projection of U in K, and we will denote it by pk of U. So pk of U denotes this U star from the theorem. Okay, so with those notations, we have the following proposition, is that the projection on a convex so does not increase the distance, meaning that if you look at the distance between pk of U and pk of V, it will be less than the distance between U and V. So we are going to prove that. Okay, so we are going to prove this result. The proof starts like the proof of the uniqueness for the previous theorem. So we will write that for, okay, you have that U minus pk of U. We take the scalar product with W minus pk of U. This is non-positive for all W in K. And you have the same thing for a V. Okay, so let's write here with pk of U, and let's choose this one to be pk of, sorry, it's V. Sorry, it's V. So here it's V and here it's U. Okay, and I do as before. So I will obtain that U minus pk of U scalar with pk of V minus pk of U is non-positive, and V minus pk of V scalar with pk of U minus pk of V is non-positive. Now I sum up these two equations. So I multiply here by minus and here by, so this and this. And then I sum up, so I obtain that U minus pk of U minus V plus pk of V scalar pk of V minus pk of U is non-positive, right? Okay, now I just okay, I'm just going to put some parts in the right-hand side, and I obtain that pk of V minus pk of U, pk of V minus pk of U is less than U V minus U scalar pk of V minus pk of u. What can I do with that? I will apply Cauchy-Schwarz inequality. So here I got pk of v minus pk of u square is less than, and here, thanks to Cauchy-Schwarz inequality, I obtain v minus u scalar pk of v minus pk of u. All right, so finally, dividing by pk of v minus pk of u, I obtain the result. So next, the next proposition focus on the case where K is a closed subspace of H. So in this case, you have that you have an equality, and you have that u minus pk of u scalar v is equal to 0 for all v in the subspace. All right, so what happens now if K is not only convex, but it's a linear subspace also? Okay, so it's stable by addition and multiplication by a scalar. Then in this case, I can write that u minus pk of u scalar, let's say w plus, so w this is the same that u minus pk of u scalar w plus pk of u minus pk of u. So since the K is a linear subspace, this belongs to K. So this is non-positive. And also I can do the same for instead of W, I take the same, but I look at minus W. And this will be, I can do the same here. So minus W plus pk of u minus pk of u. And again, this belongs to K because it's a subspace, linear subspace. So at the end of the day, this is also non-positive. So this quantity is non-positive, and minus this quantity is also non-positive, which means that finally, for all you have that u minus pk of u w, because this is non-positive and this is non-negative, so it's 0. All right, so when instead of just being convex, it's a linear subspace, you have this equality. So the next section deals with the Riesz representation theorem, or Riesz-Fréchet, Stampacchia, and Lax-Milgram. So today we are going to focus on the Riesz representation theorem, which says that when you have a linear functional continuous, so on the dual of H, then you can always find a U, and this U is unique such that when you take the product scalar U with V, it is the same thing that phi of V for all V in H. And that's what we are going to prove now. Okay, so we start with, we define a linear subspace of H by this is the kernel of phi. Okay, so you have a function phi in H prime, and you define M as the reciprocal image of 0. Okay, so if M equals H, then U equals 0, and that's it. Okay, so from now on, we assume that M is different from H. So, so if M is different from H, let's pick up W0 that belongs to H, but which not belongs to M. All right. So phi of W0 is non-zero. And then let W1 be the projection on K of W0. And finally, let W be, right, I will choose W0 minus W1 divided by W0 minus W1. Okay, now, first of all, you have that. What is the value of the norm of W is 1. Okay. And by construction, for all V in M, if you look at V scalar W, this is what? This is 0, okay, because W1 is the projection of W0 on M, and so, yeah, this is M, of course. We didn't talk about any K here. This is M. All right, so this is 0, okay? Because here W is W0 minus W1. So by definition of the projection, you have that 0. Okay, in particular, W doesn't belong to M because W equals 1. And here it's 0. All right. All right. So next, okay, now for all V in H, we consider H, so this is depends on V, will be V minus here. Okay, I define V minus phi of V divided by phi of W times W. So if I look at phi of HV, if I look at phi of HV, this will be phi of V minus phi of V, and this is 0. So let's write again this. So I define HV as V minus phi of V divided by phi of W times W. So phi of HV equals 0. So HV belongs to M, right? All right, so now since HV belongs to M, you remember that W times Z equals 0 for all Z in M. So now if I look at WHV, this is 0 because HV belongs to M, but this is also WV minus V W. So so here, this is the scalar product. So this is 0 because HV belongs to M. And also, so here I just took the scalar product here. I obtained that because remember that WW equals 1. All right, so finally, what do I get? I get that for all V in H, I got WV equals phi of V divided by phi of W. So if so putting phi W in the other side, I get that phi W V equals phi of V. So I just need to put that U, and the proof is complete. All right, so what we did, we look for a U here. We defined M as the kernel of phi. Then we assume that M is not H. If not, you choose U equals 0. And so you start with a W0, you choose W1 to be the projection of W0 on M, and you normalize. So you choose W to be W0 minus W1. So this will have a norm of 1. Okay, so by definition of the projection now, you have this. All right, and now if you consider these things for all V, when you apply phi, you have 0. So this means that HV belongs to M, and so you can take the scalar product WHV. This is 0, and this allows you to find our U. So there was a question why WV equals 0 here. So I repeat that. In fact, M is a closed linear subspace of H. You can check that. It's closed and it's a linear subspace. And so because phi is continuous. So here by since W1 is the projection of W0, and since M is a linear subspace of H, you have that this quantity is 0. All right. So in fact, I forgot we need to prove also the uniqueness. So let's do the uniqueness. So assume there's two such a U. So assume that U1 V equals phi of V for all V H, and the same for U2. Okay, this means that U1 minus U2 V equals 0 for all V. So if I choose V equals U1 minus U2, I obtain U1 minus U2 square equals 0. So U1 equals U2. And now we're done.